second semester of this academic year were given by the guru near Sloane about interesting OEIS stuff.
Thank you, Duran. I have a talk with slides and things like that, but I have some music I want to play to begin with that I will do first so that I can concentrate on the slides. So this is a piece of music which is a sequence submitted by a Frenchman called Claude Lenormand that I'll get to later, but I want to play this. I suspect he's not alive anymore. He sent it about 13, 14 years ago. And so on. Its speakers aren't adequate and I can't connect up to this for some reason. And but I'll come back to it in a minute. I'm also going to talk about a new variation on the famous Ulam-Warburton cellular automaton, which is one of the easy ones to analyze. The classical one is on squares, and it grows like this. And it's a cellular automaton that's infecting some squares in a very simple way, and there's a simple rule for it, and we understand everything about this. It's very easy. When it gets to a power of 2, it starts growing from the corners in a predictable way. This is the classical Ulam-Warburton cellular automaton, well understood. And there's a new version someone sent in to the OEIS quite recently, where instead of using a rook to move, you use a knight. And I'll come to that. So I'm going to stop this. And minimize. Produce a talk and play slideshow. And this is a slightly modified version of the talk I gave during the blizzard in November when there were 4 people. 2 people besides Susanna and Jerome. And Minja, I think.
Was I here?
There was almost nobody else here. You were there?
Yeah.
Thank you.
Yes.
Because I didn't meet anyone.
Yeah.
Oh yes. So on the blackboard, which I'm never very good at using here, I started off by putting up this sequence. I staggered it, but the staggering didn't work. So I imagine I'm writing on the blackboard, and I write down, this is a very simple sequence, and it goes 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, blah, 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 blah. 1, 6, 3, 8, 4, 3, 2, 7, 6, 8, 3, 6, 12, 24, 48, 96, 192. And you can see that most of the time it's doubling. And the question is, what's the rule for this? After a while, we get back to 1. And then 2, 4, 8, 16, 32, 6, and it cycles. It's periodic. But what's the rule? I'll come back to this. Imagine I just wrote this on the blackboard as an introduction. It's a very nice sequence. Okay, so the talk, I'm going to talk about various things as the outline. I'm going to begin by telling a story, a letter I got last March from someone who used to be an editor at the OEIS, who said that These days he doesn't use the OEIS much because he's an algebraic geometer. But he was very happy to see that it's still running, and he said that he wanted to tell the following story. When he was in high school, in Oregon in the 1990s, he loved mathematics, but he had no one to talk to, and his teachers weren't very good, and so on. And finally, he discovered the OEIS, and he got involved, and he started sending in sequences. He was an active contributor, and then he became an editor, and he had a wonderful time, and that led him into mathematics. And then he went to a famous college to get his degree, and another famous place to get his PhD, and now he's a professor at a place not far from here, where he is doing algebraic geometry. But he says that he wanted to thank me for encouraging him. He said without the OEIS, he would never have become a mathematician.
Too bad that you became a raboter.
Instead of a combinatoric number theorist. So these are some important things. I thought that was a really good story. I was very happy to see it. Another thing that's come up, I just had a birthday, and I've been running this OEIS since 1964 in various versions, and there's a question, I don't have anyone to take over from me should anything happen. So there's the question about the succession. I don't have anyone to take over the control of the ship, the starship, should anything happen to me.
But like Queen Elizabeth, you are immortal.
Well, Hilary Orman, who's one of our supporters, she says, get a young person, get Prince William instead of Prince Charles. But I really am seriously worried about this question. I don't have anyone. So, it has to be somebody who's very familiar with the OEIS and has a good command of English and computers and mathematics and all those things. And perhaps somebody will see this video when it's posted and have some suggestions. It's an important unsolved question. So, Claude Lenormand, back in the year 2000 and so, he was a contributor, he sent in many sequences, and when we reached 100,000 sequences, we had a birthday party for it was the 40th birthday of the OEIS. And so we had an E-party. I invited everybody to send in photographs and quotations and so on. And Claude Lenormand said, long life. And the other day I found a letter from him in a pile that I'd overlooked. And it was a letter from November 2003, and he suggested two transformations of sequences. The first one is what he called the runs, or what I call actually the runs transformation. So if you're tossing coins, and you get a head, and then two tails, and a head and a tail, you look at the runs. You have a run of 3 heads, and then a run of 2 tails, 1. So you write down the lengths of the runs, and you get 3, 2, 1, 2. That's the runs transform, the lengths of the successive runs. And there's a famous sequence called Kolakowski's sequence, which has the property that it's its own runs transformation, and it's over the alphabet of 1 and 2. So you start off with 1. That means the first run has length 1. It's its own runs transformation. So that means we've got to begin with a run of length 1. And we're only using 1s and 2s in this alphabet. So the next term has to be a 2. And what's more, because it's a 2, there have to be 2 2s, and so on. So that's Kolakowski's sequence. It's sequence A2 in the OEIS. And there's a famous unsolved question about the relative density of 1s and 2s. It's an open question to prove that 1s and 2s are equally dense. And then there's another sequence, Ulam's sequence, which has the same property. It's its own runs transformation, except now we have a different rule. The rule is it must be non-decreasing. And for this one, there's a very simple formula. The nth term is essentially a constant times n to the golden ratio minus 1. So that's the Run's transformation. But then he had, and that's old hat, but then he had another idea, which he called the raboter transform. A rabot is a plane in French. And the idea is, you apply this to a sequence, you look at the runs, and you shorten each run by one term. So here's Golom's sequence. It goes one, there are 2 2s, there are 2 3s, there are 3 4s, 3 5s, and so on. So it's got runs of lengths 1, 2, 2, 3, 4. The transform is you shorten each run by one term. So this is a run of length 1. That goes away. We've got 2 2s and we lose one of them. We've got 2 3s and we lose one of them. We've got 3 4s and we lose one of them and we get 2 4s. So this sequence becomes that sequence. And I don't know any formula for it. It should be a simple description. I don't have one. So that's the Run's transform. The Run's transform of any word or sequences. You look at the successive runs and you shorten them by one term. So I thought, why not look at the binary expansions of numbers? So take 12. The binary expansion is 1, 1, 0, 0. So shorten the runs by 1. So we're going to lose one of the 1s and one of the 0s, and we get 1, 0, which is 2. So we raboter 12, and we get 2. So apply this to or n to all the numbers, and you get a sequence. For instance, 1, 0, the 1 goes away and the 0 goes away, so we're left with the empty string, which I've denoted by epsilon. So when you raboter n, you get this sequence. And that's the sequence I just played. I think it's a nice dirge in his memory. I don't know if he's still alive. I'm pretty sure he's not. He doesn't answer his emails, and there are some obituaries of people with that name, but it's not such an unusual name, and so I haven't been able to trace it. So this is the result of applying the planing operation, the raboter operation to n. You get this sequence. And there were a number of so I was interested to see, for instance, what's the average size of the number you get after you've applied this transformation, and also, if you repeatedly apply it, how long before you get to the empty string? So how long does the thing survive? So that I called the Cutts resistance. And there's a conjecture, which is still open, that it's proportional to square root of n. So you start off with a large binary number, you raboter it over and over again until you get down, until there's nothing left. The conjecture is that that should be about square root of an over pi. There was another conjecture, which Daron kindly took care of right after the talk, which was how big is the result of applying the transformation once on the average. And the data suggested there was a simple explicit formula for it. It was about 3 halves to the k minus 1 for a number with k plus 1 bits.
And you're not extended to arbitrary base, right?
Ah, aha.
And also to powers?
Yeah.
Aha. Good. Let me So that's the raboter transform. And there's the inverse transform. What if you blow up all the runs? Expand all the runs by one term. So instead of 12, 1, 1, 0, 0, it would become 1, 1, 1, 0, 0, 0, which would be 7, 8, 56. And down to the top there. So it's the inverse transform. It's a left or a right inverse or something. If you first apply this, and then a raboter it, you get back to where you started. And I conjectured there's an upper bound on the expanded version, which is about 9n squared over 5, and Maximilian Hassler proved that that was true. And there's a conjecture, Jerome, if you will. What's the average size if you take a number in the range 1 to 2 to the k and expand it? The conjecture is that the average is exactly 2 to the k times 4 times 3 to the k minus 1.
So that's exact and approximate. That's an exact
Yes,
formula.
yes. A conjecture.
Yeah.
Yes.
So an exact conjecture.
So
So
that's
2 to the power k times 4.
Sorry, yeah.
2 to the power k times 4 times.
2 to the k times 4 times 3 to the k minus 1, close parenthesis. And then, if I had a better setup, a louder speakers, I would now play the dirge, but I played it at the beginning. So, when was this? The other day, one of my favorite contributors to the OEIS is a television reporter and producer called Eric Angelini in Brussels. And let me show you what I think he suffer like all of us do from insomnia. But here's something he thought of. It's a process. You take a number and you can do the following transformations to it. Your choice. Okay. So we take, I'll give you an example. Suppose the number you started with, I was going to put the year 2018, but there are more possibilities. It displays it better. If it's 20218, 20,218. Let's start with that number. Okay? We have a choice. Here are the things we can do. We look at a substring, say 21. And then, if it's even, we can divide it by 2, just sitting there. And if it's odd, we can, whether or not it's even or odd, we can double it. We have a choice. So that 8, we could change to a 16, which would be, where is it? That would give us 202116. It's down here, and I put an exclamation point after it. Because what we've done, we've changed that 8 to a 16 in its place. So that's increased the length by 1. This is a slightly strange operation. So here are the things you can do. You pick any substring that doesn't begin with a 0. If it's even, you can divide it by 2. And if it's odd, you can either divide it by... Sorry. If it's odd, you can only multiply it by 2 if you want. So that 21 could become 42. And that's down here somewhere. Thank you. But if we took 218, we could divide it by 2 as it stands, and we get 20109, which is there. And that initial 2, we could make it into a 1, so we get 10218, or we could double it and get 40218. So we can get all of these things from 20218. It's a bit strange, this, isn't it? Clear? So the question is, there are lots of questions you can ask about this. If you repeatedly apply this, you start with 1, what can you get to? Anyway, so I thought of a name. Probably I shouldn't make jokes in French. But it's a game, like the game of Sprouts. And Sprouts are chou de Brussels in French, and Eric Angelini lives in Brussels. and there's a choice involved. So it seems natural to call it choix de Bruxelles. So that's the operation we're doing. It's a multiple choice thing. You start with a number, you can apply any of those operations, and you get a whole selection of other numbers. And the questions are, what do you get to if you start with 1, for example? Oh, so here's a small example. 16. You can do nothing if you want. You can double the 1. You can halve the 6, and you get 13. You can double the 6, so you get this is rather bizarre. You get 1, 1, 2. You double the 6, and you get 12. And you write it where the 6 was. And you could halve the 16 and get 8, or double it and get 32. So 16 goes to any of those 6 numbers. Is that clear? So if you start with 1, what can you get to? So can you get to 2? Yes, obviously you can double 2 and get 4. You can double 4 and get 8. You can double 8 and get 16. And then you can do all those things that were on the previous slide. But can you get to 3? Well, somebody came up with a string of 88 transformations that finally ended up at 3. But then Lorenzo Angelini, Eric Angelini's son, came up with a string, a path, from 1 to 3 in 11 steps. And you can prove that's optimal. And you can get to 5. No, you can't get to 5. This is the whole point. You try really hard, and you cannot get to 5. And there's a theorem. You can reach n from 1 if and only if n does not end in 0 and 5. 0 or 5. And if it does end in 0 or 5, those numbers are all connected. The graph has 2 components. And I now know a lot about this graph. I know how long it takes to get to n for any n, very precisely.
So you can do it in any base, not just base 10.
Yes, you can do it. Base 2 is boring because it doesn't change the weight. So we didn't look at other bases. Base 10, this is an instance where base 10 seems more interesting than any of the other bases. Yeah, so I want to talk now a bit about coordination sequences. These come up in all kinds of situations. They come up in chemistry and graph theory and so on. And
you described what you had just done as a game, but it isn't actually a game.
It's not really a game, no. No, it's one person.
It's one person game.
Yeah, a game is not a bad word. I just wanted an excuse to mention sprouts.
Okay.
I mean, you can play sprouts on your own, I guess. So I have postcards as a poster of sequences with nice pictures. And one of the pictures in the poster is this. This is a tiling of the plane. It's one of the regular tilings. It's a tiling of the plane by hexagons and triangles. And each vertex has a neighbor, which is a hexagon, and 4 neighbors, which are triangles. It's a tessellation of the plane, whose name is 333, 3 to the 4th 6. It's one of the regular tilings of the plane. There are only 11 of them, so it's very special. And the different colors here show the coordination sequence. I've got a better picture here. Yeah. So here's the tiling. All the vertices are equivalent. The group is transitive on the vertices. So pick a vertex, any one, and we pick this black one. And you ask, how many vertices are adjacent to it? It's the coordination number if you're a chemist, and it's adjacent to 5. So we get a sequence. We've got 1 at the starting point, we've got 5 neighbors, and then we've got 9 points that are at distance 2 from there, 15 are at distance 3, and that gives you the coloured shells. And the question is, how many points are there in each shell? That's the coordination sequence for this. And this is a very useful kind of thing. It enables you to identify structures, to find out how dense they are, and other useful properties. And so for this one, there was a conjecture, I think by Chavy, that the numbers in each shell satisfy a recurrence, that A of n plus 5 is equal to A of n plus 24. And that it was just a conjecture. So here's the general definition. We take a graph, and it's nice if it has some structure to it, not a totally random graph, but you could do it with a random graph. Pick a graph, pick a point, and look at how many vertices are there at edge distance n from the starting vertex. And that's the coordination sequence. And if you were looking at the square grid, just ordinary graph paper, you pick a point, it's got 4 neighbors that are red, it's got 8 green neighbors, and 12 at the next layer, and you get 4 more points at each layer. So the sequence is 1, 4, 8, 12, 16, 20, 24, 28. Sequence A, 8, 5, 7, 4. Its generating function is just generating, it's a Jacobi theta series theta 3 squared. It's the, if it was one dimension, it would go 1, 2, 4, I mean 1, depending on what we're counting. 1, 2, 2, 2, 2, 2, and here we're getting the square of that. So, if you walk from here down the hill to Johnson Park, there's a zoo. Near the zoo, you'll see the road is tiled with bricks in this pattern. And I walked by it many times, and I thought, well, what is this structure? So I worked out the coordination sequences. If you look at it, you see there are 2 kinds of points. There are points that have valency 4, like that one, and there are points that have valency 3. So there are 2 coordination sequences, depending on which point you're sitting at. If you're sitting at a point of degree 4, you look at the coordination sequence, and it goes 1, 4, 8, 12, 16, 20, 24, which you have seen before, because that's the same as the coordination sequence for graph paper. But this is a different structure. And if you look at the degree 3 point, its coordination sequence is that. So you look them up in the OEIS, which is what you do when you get into an interesting sequence, and you find that it's the same pair of coordination sequences as the chirotiling, which is a paper that Chaim Goodman-Strauss and I have just published in Acta Crystallographica, analyzing this structure. And to see that it's the same, if you take the thing in Johnson Park and contract all of the diameters of the squares by 50%, you get the chirotiling. And so the chirotiling, I'm told that you see this on the streets of Cairo, and it's not regular because it's got 2 kinds of vertices, but it's 2 transitive on vertices. And again, it's got vertices of degree 4, vertices of degree 3. There are the coordination sequences. So Chaim and I thought, why is one of these the same as the coordination sequence for the square grid, for graph paper? And we thought,
well, the Johnson Park tiling has a name?
It's the same, no, I don't know what it's called. I don't know what bricklayers call it. But it's equivalent. The tiles have 5 edges, if you look at them. They're not really bricks. Anyway, so all of the tiles are equivalent, and there are 2 kinds of vertices. And they're pentagons. They're not quite regular pentagons, but you can distort them a bit. Anyway, so we thought there should be a simple proof. This is definitely different from the square grid, and yet it has the same coordination sequence half the time. Why is that? So we came up with what we called, initially, we called it a child's colouring book method.